Hey guys, today we're going to be doing parallel circuits in RLC. So let's just get straight into it. But first, let's start with the refresher here. Okay. Alright, so we have a resistor. And the equation for a resistor is V equals IR. Probably the most popular formula in EE. Then we have the inductor. And this formula is V equals L di dt. And we have a capacitor. And the formula for this is I equals C dV dt. Okay? And then parallel RLC circuit is going to be where all the components share the same two nodes. So at the top here, draw a resistor, an inductor, and a capacitor, right? So this is parallel, and typically when we're analyzing these circuits, we're looking for the voltage across here. And for series, we're looking at all of them sharing the same current. So resistor, inductor, and capacitor. Sorry about my bad drawing, but as you can see, typically we'll add like a voltage source here, and as you can see, they all share the same current, right? So now that we've gotten that out of the way, let's move on to actual analysis. Or let's start with the characteristics of these circuits. So we have a parallel circuit. Okay. So I'm going to redraw it, with the resistor RL for inductor, and then C, capacitor. Okay, they all share the same nodes. Alright, we want to find the V here, because typically, if we know the V here, we can find everything else. We can find the current through resistor, current through inductor, current through capacitor, we can find everything. So, let's use KCL. KCL at this node, right? So we're getting used to this. Alright, and so we would have the current through the resistor plus the current through the inductor plus the current through the capacitor, and that equals 0, right? So we know that the current through a resistor is just V over R, right? And for the inductor, it's a bit tougher because it's not strictly in term. We actually have the derivative of the current, so we're gonna have to do some manipulation here. So I'm gonna move the L to the other side. Actually, I'm gonna move the dt as well. So we get di dt, or 1 over LV dt equals di. And so if we integrate both sides, take out the L, 0 to t, V. Sorry about that. So t, V dt equals di. And this is from I initial and I of t. So integrating, we get 1t v dt equals I of t minus I initial And so that would get us IL of t equals 1 over L 0t v dt plus I initial, I of 0, the starting current through it. There, let me add that. All right. And the capacitor, also much more easier. It's just C dV dt. All right. So, if you put them all together, we get V over R plus 1 over L 0t v dt plus I initial plus C dV dt, that equals 0. This should be our KCL equation with all of the stuff. So what I'm actually going to do here is I'm going to derive both sides, right? So we got 1 over R dV dt. Derivative of this, it's just an integral, so we can just get rid of that. So we have 1 over L V, and this is a constant, so that just goes away. And then we have C d squared dt squared equals 0. Alright, so I'm going to rearrange some stuff so we can get into our characteristic equation. Okay, move the d squared to the front, divide everything by c. And then we get this equation right here. Right here, this is our characteristic equation for parallel RLC. And so typically in the second orders, you'll find that you can put them into this form: 2 alpha plus, or dVdt plus W naught squared, this is the natural frequency, equals 0. And we'll go more in depth into what these are, because these are pretty new things, right? And so let's try solving the differential equation, right? So we had the equation d squared v dt plus 1 over RC dv dt plus 1 over LC of v equals 0. And so we're just going to guess that the solution, or guess, is, it takes the form a e to the st, right? We're just going to guess. Alright, so if we do that, we get a e to the st times s squared plus 1 over RC. Oh, let me actually just put a to the e to the st times 1 over RC times s plus a e to the st plus, or not plus, times 1 over LC, right, equals 0. And so if we divide both sides by e to the st, we can simplify this to s squared plus 1 over RC s plus 1 over LC equals 0. Alright? And so you can see that this right here is our characteristic equation just in the s. And so these s's will be the solution to, or that would be the roots for our exponential here. And so, oh, one sec. So we'll see that v of t will equal a e to the s1t, our first root or first solution from this quadratic, and b e to the s2t, right? And so just keep moving down. All right, so we have that, we have our solution, but what if our roots are complex? Because we know that sometimes in a quadratic, the roots will be complex. So what happens then? Okay. And so we're gonna let S be some real component plus B, J. This is our real part, and this is our complex part. Using J, same thing as I, just in EE, we typically use J. Alright, so that means we would have A to the, or times E to the A plus BJ times T from our solution. Alright, and then we're going to split this up because when you add, when there's addition in the exponent, we can multiply them out, right? So this would just be AE to the AT times E to the BJ, right? And so this is where I'm going to show Euler's identity. Okay, and so what this is, it's just saying E to the J theta equals cosine theta plus J sine theta, all right? Right, and so there's a bunch of complex math behind this, and we're going to use this complex math. We don't need to know it, how it works, but we just need to see that when we have a complex component inside the e exponential, we actually can find sinusoids, right? And so if you change that in, we get e to the AT times, or sorry, I forgot the t here. Let me just erase that. J times t, right? We actually get cosine bt plus j sine bt. And so we have, you'll see here we have a sinusoidal component here, right? And so that means if our roots are complex, we will have a sinusoidal looking form for our solution. So if we continue the math here, if we do it for the other root, then we would get the form v of t equals a cosine, or a e to the negative at. We'll get to what the a here in the next part. Cosine bt plus b e to the negative at sine a of t. Okay. So now that we know that, we can find our parameters, right? So we have the parameters of an RLC circuit, specifically the parallel version, because that's what we're doing today. Okay, so I showed you this before, or just exposed you to it. This was our original characteristic equation, but typically in second order systems, in any second order system, like spraying or dampening, just any, or not that, any alternating thing, can simplify it to this: S squared plus 2 alpha S plus W naught, which is the natural frequency squared, right? And so, if you compare this to our circuit equation, we can find that alpha is equal to 1 over 2 RC, and that our natural frequency is equal to 1 over square root LC. Alright, and so these are very important and makes finding our solution a lot more easier, because you could try and solve this quadratic, but you know, the quadratic formula is kind of annoying to type in your calculator. So here we have the parameters of the circuit. And these are really important because if we know these parameters, we can know exactly how the circuit will behave, right? So if we know the parameters, sorry about my bad handwriting, we know how the circuits will behave, okay? And so, go into more in depth, or let me make a new page. Okay, so that brings us to damping, all right? Damping. So the 3 types of damping, okay? We have underdamped, critically damped, and overdamped. Okay? And so, let's go on to when we know our circuit will be these 3, right? So, our circuit will be underdamped when alpha is less than our natural frequency, right? So back to, let me write alpha again. So 1 over 2 RC, and W naught is 1 over square root LC. So when our alpha is bigger than our natural frequency, that means our circuit is underdamped. So what this means is that we'll have complex roots. So like some examples would be 3 plus 1j, 2 plus minus 6j, or any sort of conjugate, right? And so what that means, as we talked about before, is we would have the solution form of ae to the alpha t cosine wd t plus b negative alpha t sine wdt. And so you haven't seen WD, and so what WD is, or the damping frequency, or the damped frequency, is square roots of our natural frequency squared minus alpha squared, right? And so that's the underdamped case, when our alpha is less than our W naught, because alpha is typically the strength of your dampening. So if it's not strong enough, then it'll actually oscillate, right? So let's go on to critically damped. And so this happens when our alpha equals W naught, right? So the cool thing about critically damped is that this causes the circuit to go as quickly as possible to 0, or its resting point, right? So basically this means that we will have real and repeated roots. So some examples, you'll have like negative 500 or negative 2 or like negative 1000. You'll typically see in your problems that they're much larger than these numbers, but I'm just throwing them out there. So this will take the solution form of, let me just block that out. So v of t equals a e to the negative st, and or plus b times t negative st. Where this t came from is some diffie q stuff, not really in the scope of circuits, but just know that it is there and critically damped. Alright, and so that brings us to overdamped. And so if you look at the others, then this means when A or alpha is not equal to, is greater than our natural frequency. So this means we have two real distinct roots. Okay? Some examples be like negative 3 and 2, negative 2, negative 1000, and negative 4000, something along those lines. Again, you'll typically see on the orders of like 10 to the power 3 or 4. I'm just throwing some numbers out there. Right, so this should take the solution form. This was our first case where it was simply v of t equals a to the e s1t plus b e to the s2t, right? Where s is equal to negative alpha plus minus WD. And in this case, our damped frequency, or WD, is just alpha squared minus W naught squared. Notice how in this one, the alpha is first because it's bigger than our natural frequency. And this just makes it so that it's not a complex number, because then if natural frequency was bigger, then this would be a complex number with an I. Alright, so let's go over an example. So where's the hand tool? Alright, an example. So, what type of damping does this parallel circuit have? Okay, so we're gonna have our resistor equal to 100 ohms, our inductor equal 50 millihenries, and our capacitor equal 0.2 microfarads. Alright, so we need to get our parameters for the circuit, and we just need our alpha and our W naught, our natural frequency. So 1 over C. Okay, and so if we plug that into our calculator, we will get 12,500 radians per second. That's the unit of our alpha, also known as a Neper frequency, some terminology you might hear. And our damped frequency, or not damped, sorry, our natural frequency is 1 over LC, square root of LC. If you plug that into our calculator, we get that this equals 10,000 radians per second, right? And so now it's time to compare alpha and maybe not. And so we see that alpha is greater than our natural frequency. So this is overdamped. Okay, and that is our answer. Hey guys, in this video we're going to be going over parallel RLC analysis and specifically the natural response. So let's get straight into it, right? So what is the natural response of an RLC circuit, right? So basically it's when the circuit is left alone, or more technically, how the circuit will respond naturally. Hence the name natural response, right? So basically what that means, another definition, is typically you'll see RLC circuits with some sort of input, maybe not a voltage source. Let me draw. Or like, yeah, current source. Okay. Typically see an RLC circuit, right? What a natural response is basically there is no input. No input, right? So basically all you're left with is just these three in parallel. All right, so now we know that, let's just go straight into an example. Okay, so let's say we have this circuit. Okay, the inductor, and then a resistor. Okay, and we want to find V, right? We want to find V of t, okay? And we're also given V0 plus equals 12, and the initial current through the inductor, positive, is 30 milliamps, okay? So let's start with finding the parameters of this circuit. Oh, sorry, let me write down the values. So we have 0.2 microfarads, 50 millihenries, and then this resistor will be 200 ohms. Okay, so we need to find our alpha and our natural frequency, right? So alpha is equal to 1 over 2RC, as we saw in the parameters video. And so if we put that in our calculator, we get that alpha is equal to 12,500 radians per second. And this, our natural frequency, is equal to 1 over the square root of LC, which equals 10,000 radians per second. All right? So, comparing our alpha and our omega naught, we see that this circuit is overdamped. Okay, it's overdamped. So that means our solution will take the form V of t equals a e to the s1t plus b e to the s2t. Okay? And so let's find our s1 and our s2, right? So s1 is equal to negative alpha plus our damped frequency. S2 is equal to negative alpha minus our damped frequency, right? Nope, I'm completely wrong. I'm so sorry. Never mind. Spin that back. Right? So, now what was our damped frequency again? Well, in our overdamped case, WD is equal to alpha squared minus omega naught squared, right? So if we plug that into our calculator, the square root of 12,500 squared minus 10,000 squared is 7,500. So knowing that, we know that this is negative 5,000, and this is negative 20,000. Okay, so let's rewrite our v of t. We have now that v of t equals a e to the negative 5k times t and plus b e to the negative 20k times t, right? And so next, we need to start finding our unknowns, our a and our b, all right? So we need to find two equations. So we know that our v of 0 plus equals 12, right? And so we want our v of 0, right? We know that this is equal to 0 z plus because in a capacitor cannot change voltage instantly. All right? So that means this is equal to 12. So we bring it into our form equation. We have that 12 equals a times e to the negative 5k times 0, because we're inputting 0 as for t, plus b e negative 20k times 0. And that just simplifies to 12 equals a plus b, all right? So that's our first equation. But we have two unknowns, so we need our second equation for each unknown, right? So let me redraw the circuit. Okay. So let's start with our KCL here in the top node, right? So we know that the current through the resistor plus the current through the inductor plus the current through the capacitor should sum to 0 via KCL, or Kirchhoff's current law. Okay, and so let's just start with what we know. We know that V over R is for the resistor. Let's just keep our inductor as I of L. And we know that C dV dt is for the current to the capacitor. Alright? And so we actually have the current through the inductor here. We know that it's IL 0 plus equals 30 milliamps, right? And for similar to the capacitor, we know that inductors cannot change current instantly, as opposed to capacitors, they can't change their voltage instantly, right? So let's plug in for 0, right? Or let me just write this down. We know that IL of 0 equals IL 0 plus, which we know is 30 milliamps. So we know our V of 0, and then our IL of 0 plus C dV 0 dt equals 0. So let's just move everything to the other side and just isolate this dV 0 dt. So we should get -1 C P O R. This is just the initial. IL 0. Alright, so this is our dV dt. And so let's bring in our form equation, which was V of t equals a e to the negative 5k, right? Yeah. 5k plus b e to the negative 20k t. Alright, so let's derive it. So we have dv dt equals negative 5k a e to the, I'm just going to write s1 because just to save time, minus 20k b e to the s1 t. And if we plug in 0, our initial dV dt, it simplifies to negative 5k a negative 20k b. Alright, and so we actually know our initial voltage here because of this, right? So if we plug in that, we get, that dV0 dt equals negative 450,000. And so that also equals negative 5,000 times A minus 20,000 times B. All right, and so now we have our second equation. Let's bring down our first equation, which was 12 equals A plus B. Plug the system into our calculator, and then we should get that A equals 26, and b equals negative 14. So bring that back into our form equation. Our final answer should be v of t equals 26e to negative 5,000 is t minus 14e to the negative 20,000 times t. And that is our final answer. Hey guys, today we're going to be going over series RLC, and more specifically the natural response, so let's get straight into it. So, series RLC circuit, we have all the components share a single current, so they're in series, and the circuit looks a little like this. Depending on the circuit, sometimes you'll see a voltage source, current source, or just a short, and that's going to determine whether we're analyzing a natural response or a step response. So a natural response, as we saw in parallel RLC circuits, is going to be no input. So in this form, that means we'll just have a short as our input with an R, L, or C. Okay? So knowing this, let's get our governing equation. Okay? Governing equation. Okay? So I'm going to do a KVL clockwise here. I'm going to start at the resistor. So voltage across that is IR. Notice how I'm not putting any subscripts or like specifically the current through R, because all the components share the same current. Next, I'm going to do the voltage across the inductor, and that is L di dt. And the voltage across the capacitor, which we know has the equation I dv dt. If we do math similar to the inductor in the parallel case, we find that the voltage across the capacitor is 1 over C, 0 to t, I dt, plus the initial voltage, and that equals 0. Okay? So, like the parallel case, I'm going to derive both sides. So I have R di dt, L d squared I dt squared, plus, and this is just an integral, so we're just going to remove the integral because we're differentiating. 1 over C times I, and this is a constant, so that's just going to disappear. So after rearranging, we get di dt squared, and I'm dividing both sides by L. R over L di dt plus 1 over LCI equals 0. And so what we're going to do here is we're going to put it in the form of our second order characteristic equation, which is di dt squared plus 2 alpha di dt plus 1 over LC I equals 0. So if we solve for alpha, or sorry, not LC, W naught squared, if we solve for our alpha and our omega naughts, we see that alpha equals 2 over RL, or sorry, R over 2L, and our W naught is equal to 1 over square root LC. And so just like parallel case, we're going to use these to find the type of damping in the system, and that's going to show how the form of our solution will be. So let's go straight to an example. Okay, so we have the following circuit. We have a resistor, an inductor, a capacitor, all in series. We have 560 ohms, 100 millihenries, and 0.1 microfarads. Okay? And we also have that the initial voltage of the capacitor equals 100, and the initial current through the inductor is 0. So let's find the damping, or the type of damping in this circuit. So let's start with our parameters, which are alpha and W naught. And so we know that these equal, or alpha equals R over 2L, and omega naught is equal to 1 over square root LC. Put this in our calculator. We find that alpha, is equal to 2800. Sorry, bad handwriting. It's equal to 2800. And our W naught is equal to 10,000. And these are in radians per second. And so if you compare these, we see that alpha is less than W naught. Oh, sorry. So that means the system is underdamped. Okay? Knowing that it's underdamped, we can now guess, or know that the solution for I of t, we're solving for I of t, sorry, will be a e to the negative alpha t cosine WD, or the damped frequency, plus b e to the negative alpha t sine WD times t. Okay? So let's start making equations for unknowns. Alright? So let's say, or let's have the initial current, or I of 0. If we plug in 0, we get A, because this will turn into a 1, and this will just disappear. So A is equal to the initial current. So that A is just 0. Because we know that IL is 0. And everything shares the same current in this series circuit. Okay, so now we need to find our second equation for B. So I'm going to start by deriving both sides. And there's a lot of math. So in algebra, with this, all the product rules, so I'm just going to give you the form. So we have negative alpha A plus damped B. So this is the form. And so let's find our damped frequency first. And so our damped frequency is a square root of omega naught squared minus alpha squared. And that equals 9600 if you plug it into your calculator. Okay, so now we have di dt. We know that a is 0, so we have that di dt equals 9600 b, or more specifically di 0 dt. So now, knowing this, we're going to have in our, or if you look back at our parallel case, we did a KCL at the top node, or KCL at the top node to find our initial dVdt. But for series, we're going to do a KVL around the loop to find our initial dIdt. So if we have VR plus VL plus VC equals 0, okay, we see that if we solve for, or if we rearrange some things, we have IR plus the voltage across an inductor is LdIdt, and we're just going to keep the capacitor voltage. So if we rearrange some things, we have di dt equals negative 1 over L I R plus V of C, or V sub C. And so if we find the initial, we find that this will be the initial current, and this will be the initial voltage. So di 0 dt equals negative 1 over L, and this will turn to 0 because initial current is 0 plus 100. So we find that di, if we do the math, plug in our L, we find that this is equal to negative 1000. And so negative 1000 equals 9600 B. So now we have both our unknowns. We have that A equals 0 from here, and we have that B equals 1000 over 9600, which is approximately negative 0.10467. We get that, or from here, we get that from here. Oh, sorry. We can now plug these into our equation and find that I of t, A equals 0, so all this cancels out, and B equals negative 0.10467 times e to the negative 2800 t times sine times the damp frequency, which is 9600 t, and that is our answer. Hey guys, today we're going to be going over series RLC, and more specifically the step response. So let's get straight into it. So previously you've seen the natural response where there's no input or a wire, just a short connecting the ends or the terminals of the RLC circuit. But now we're going to see that instead of a short, we're going to have most commonly a voltage source being input. So here we are. You can see that there is the input attached. So typically, when solving these problems, we're going to have to find the voltage across the capacitor, all right? And so we're going to do that, all right? We're going to start with the KVL. We're going to call this voltage VI, okay? So we have IR starting from the resistor plus L di dt plus the voltage across the capacitor. We're just going to leave it as V sub C. And then that equals VI. Okay? So we know from our capacity equation that first off, we need to know that all the components share the same current. So I is also equal to the current through the capacitor, which is C dV dt. Okay? So now knowing this, we're going to substitute I for C dV ct. I'm going to plug in here. We have RC dVc dt plus LC d squared dVc dt squared, and then plus V sub C equals VI. If I rearrange, we're going to get d squared Vc dt squared, dividing both sides by LC. So we're going to have R over L dVc dt plus 1 over L Vc equals Vi over LC. And if we remember from diffie Q, we know that y of t, the solution to a differential equation, is y of t, and that equals the homogeneous solution plus the particular solution. And so the homogeneous is the natural response, and the particular is the forcing function. Forcing function response. And as we saw in parallel, we find that our particular solution equals VI. And you can go ahead and test out VI, assuming VI is constant, of course. And we'll see that VI is in fact the solution for this differential equation. So knowing this, we find that our Vc of t is equal to Vi plus our natural response form. Okay, so let's go straight to an example. Let's say we have a circuit with an input voltage of 48 volts. We have a switch. We have a resistor, an inductor, and a capacitor. This switch will connect the circuit at t equals 0. The resistor is 1,250 ohms. The inductor has 0.1 henries, and the capacitor has 0.4 microfarads. And we're going to assume 0 initial conditions. Okay, so now what does 0 initial conditions mean? Well, this means that all initial values are 0, or basically Vc of 0 equals 0, and IL of 0 equals 0. And so we need to find VC, V sub C of t, okay? And so let's start by analyzing our parameters, our alpha and our W naught. And as we saw in our governing equation, our alpha is R over 2L, and our W naught is 1 over square RLC. So if we plug this into our calculator, we get that alpha is 6,250 radians per second, and our W naught is 5,000 radians per second. So knowing this, we see that our alpha is greater than our W naught. So overdamped. Our system is overdamped. Knowing this, we need to find our WD, which is alpha squared minus W naught squared. If we plug this into our calculator, we get 3,750 radians per second. And if you find the roots, S1 equals negative alpha plus their damped frequency right here equals negative alpha minus the damped frequency. We should get negative 2,500 and negative 10,000 as our roots. So, knowing that it's overdamped, we know that the solution will take the form Vi plus the natural response form, which is A e to the, or S1 times t plus A e to the, or not A, B e to the S2 t. And we know that Vi is equal to 48. S1 is equal to negative 25,000 or 2,500. I'm going to write 2.5K just to shorten it, plus B, which is equal to negative 10K times T. This is VCT. Okay. So let's start with finding our initial, or we already know our initial voltage through the capacitor from our assuming zero initial conditions. We know that's 0. So if we plug in 0, we find that 48 plus A plus B equals 0. Let me fix this 8. So now we need to find our second equation, and we're going to start by knowing that IL equals the capacitor current, which equals C dV dt. And so we know that this is 0 from our zero initial condition, so C dVc dt equals 0. We can just cancel this out. So we're going to derive both sides of the capacitor voltage. So the constant disappears. We have negative 2.5K times A plus, or minus 10K times B. And so here we have our two equations right here and right here. If we plug this into our calculator, we should find that A equals negative 64 and B equals 16. And then plugging them into our solution, we get that the capacitor voltage is equal to 48 minus 64 times e to the negative 2.5 kT plus 16 e to the negative 10 kT. And that's our answer.